Hi there, welcome back to the channel. Welcome to the next installment in the Back to Basics series of radio restoration. In this video I'll be tackling the AM-IF alignment. I'll explain what the IF is, I'll explain why you need to align it, we'll talk about selectivity and sensitivity and the differences between them, and I also want to give you various tools or various methods of achieving this alignment, starting with your ear all the way to an oscilloscope with a sweep generator. They used to use something called a wobulator. They also used to use something called two ears, which we've kind of lost the habit of using. But hopefully by the end of this video, you'll have various options to improve the reception of your radio. Just by the way, I'm sitting with COVID at the moment. I'm feeling better now, but it hasn't gone away completely. So this week has been a rather tough one. But nevertheless, I hope the video is still informative and I hope that you benefit from it. If you enjoy this series, stick around and enjoy the video. But before we carry on, I just want to thank the sponsors of this video, PCBWay. You'll find them at PCBWay.com. They're the people that I go to for all my PCBs, for the projects that I develop on this channel. They've got a very, very simple method of getting yourself a quote for these PCBs, and they start as low as $5 for 10. But besides the standard PCBs, they also do advanced PCBs, rigid flex PCBs. They do assembly, they do stencils. They also do CNC and 3D printing, which is just the same method as you do for PCBs. You drag your file up and you determine the characteristics that you want, and it gives you a quote, and you can then just order direct. I've used their 3D printing services. The results were phenomenal. The turnaround time is amazing. For those of you looking for services beyond these, just go to their products and capabilities. They have an enormous range of services that you can benefit from. And don't forget, they've also got a share section where you can look at projects that some of your creators have created, made available on the share section, so you can order directly from there. So whatever you need, go to PCBWay. I'm sure you'll find something for your needs. Now that we know that the radio is actually working, there's the alignment to do. And the first stage that I'm going to tackle is the IF alignment, and I'm going to do that for the AM bands. So this has got two IF frequencies going through here. One of them for the AM, which I've already mentioned, 460 kilohertz in this case. And I know that a lot of American radios use 455. Some of the German radios use 455, 456, 460, 470. It uses all sorts of frequencies, but this particular one is 460 kilohertz. And what we're trying to do essentially is take 460 kilohertz from here to there. So we want to take it from the mixer, which is the tube that produces that 460 kilohertz, through the first IF transformer, through the IF amplifier, through the second IF transformer, and through the detector diode that's on this in this tube. Now the whole idea of aligning is we're trying to get the best selectivity and we're trying to get the best sensitivity. Now, selectivity and sensitivity, it's sometimes confused. Some people think it's the same thing. It's not. And the way you tune it to give you the best sensitivity or selectivity is precisely with the IF transformers. Now I know that in this particular radio, the AM IF transformers are the top plugs. This can be on different IF cans. It can be vertically, it can be one on top, one underneath. In this case, we've got a nice neat one. It's at the back here. That's the first IF transformer primary, that's the secondary, that's the second IF transformer primary, that's the secondary. So it's nice and easy. You can get to it quite easily, which is a blessing. Now, what are we trying to do again, as I said, is trying to improve the sensitivity and selectivity of the set. What does that mean? Well, the sensitivity is the ability of the receiver to pick up a weak station and produce a discernible audio at these speakers. Now, the higher the sensitivity, in other words, the higher the sensitivity that you tune these two to, the better it will receive distant stations. So it'll amplify very weak signals better. Okay. Now here's an example. This figure gives us two bell curves which represent the passband of two different radios tuned to the station at the same frequency. If we imagine that the signal is at frequency A, we see quite clearly that both are tuned or optimized to the same frequency, but the green curve results in a stronger signal being received than the blue one. If the strength of the signal is sufficient, then both radios will receive a signal, but the green one will be less noisy than the blue one. And this will result in a better signal-to-noise ratio and then, hence, better reception. Now, the sensitivity can be greatly improved by adding an RF section right before the mixer, which our radio in this case does not have one. But it is also an important result of the IF tuned circuits of the receiver. In other words, as I said, the IF transformers. We therefore see that the relative height of the bell curve is an indication of relative sensitivity to the radio. The higher, the better. Now, selectivity refers to the ability of the radio to tune cleanly to a station that is very close in frequency to another station. In the past, there were many stations. They each sort of took up their slot, which meant that to the left of the station you were listening to, there was another one, or immediately to the right, there was another one. So you needed to actually filter the circuits to only give you that station that you were tuned to. Here's a simple demonstration of this. If you've got two stations, one is on frequency A, the other one's on frequency B, and they are quite close together in frequency. If your receiver is not very selective, then when you tune to A, part of the reception of B will come through. Now let's look at it this way. If you tune it to this line over here, you get A, okay, your blue line, you get A, but if you go down here, you see that there's quite a bit of B still coming through. See that? Quite a bit of the transmission from frequency B is still being picked up here. The difference is between there and there. It's not that big a difference. Now the same applies if you're trying to tune to station B. The station A will bleed through, you see, it will bleed through when you tune to station B. Now here's the same situation with a receiver that is more selective. While some of the adjacent signals still comes through, like if you tune to A and you look at where B is all the way down here, you're getting a bit of B coming through when you tune to A, but it is way lower than what you are tuned to. So it's so reduced that you're probably not even going to hear it, and you shouldn't hear it, because you're trying to listen to this one. You don't want to have that one coming through. Now this description of the high need for, or the need for high sensitivity and selectivity leads us to think that what we want is actually the IF passband to be extremely sharp. In other words, if you could make this blue line literally sort of all the way just down here, right? Just like almost the line itself. You'd think, yeah, that's good. That's what I want, right? Wrong. You see, the audio information needs some bandwidth in order to come through. Otherwise, no audio will come through. You'll just get the carrier wave, and the carrier doesn't give you any information. It just carries the modulated signal. So the audio signal that was modulated onto the carrier at the transmitter becomes a composite signal that spreads out from the carrier frequency in both directions. They merge spectrums above and below the center frequency. So when it passes through the mixer and becomes the IF signal, it remains as a spread above and below the IF carrier frequency. So we need to allow a small band spread of frequencies to pass through the IF filters and not just the IF frequency, which would give us no information at all. Now, here is what we really want. If, for example, we want to allow all frequencies below 4 kilohertz to be heard at the speaker, which is approximately the typical frequency span of the human speech, then this audio information is modulated on the carrier and will carry a span of 4 kilohertz below and 4 kilohertz above the actual carrier frequency. So our bandwidth that we want between the lowest frequency and the highest frequency in this case is about 8 kilohertz. Because we can't really just make a straight line down here, that's not how filters work. Filters have drop-off. We actually define a bandwidth as a certain number of dBs below its peak. So within this bandwidth, 3 dBs below to 3 dBs below above the frequency, that's your bandwidth. So all other frequencies, these should be heard quite well, and all the frequencies below that should be highly attenuated, and the frequencies above that should be highly attenuated. So if you're an audio purist, you know this is pretty bull, because you need 20 kilohertz to hear the full audio band. But remember, medium wave was not hi-fi. In fact, FM didn't go to 20 kilohertz. So this is enough for a reasonably good quality AM signal to be heard. And that's what we normally try to achieve when we align the IF stages. And that's precisely what we are going to try to do now. Now, to do the IF, we need to produce a signal equivalent to the IF frequency, which is 460 kilohertz. So I'll set it up to 460 kilohertz. I'm going to set the amplitude as low as it'll go on my signal generator. It doesn't go below 1.4 millivolts RMS, which is too high for the system, but I'll show you what I do with that next. And then we need to set a modulation, and the modulation type is AM modulation. I'm going to put a depth of 30%, and I'm going to give it a, call it a 1 kilohertz tone. That should be set, and if I click that, what's coming out of here is a 460 kilohertz carrier with 1 kilohertz audio tone modulated on it. So if I demodulate that, I should hear that tone, correct? Now, this signal is too hot, too strong for what I need, so I need to reduce it. And to do that, I've got a switched attenuator here. So my signal comes in here and comes out there. This switched attenuator is a project that I designed and built some time back, and I can attenuate it by 3 dB, 6 dB, 12 dB, or 24 dB, or the combination of those. So to start off, I'm going to leave it at that. I need to make the signal as small as possible in order to avoid the AGC, the automatic gain control, from affecting the tuning. So I'll explain that when I show you the schematic again. So what I'm going to leave it at is I'm going to leave it like that, and then I'll start attenuating it till I hear the tone, but it's not strong. And the way to work with these attenuators is you keep summing. You've got 3 dB and 6 dB. I've clicked 6. If I click 12, I now have 18 dB. I'm not sure how much I need, so I'll leave it at that for now. Now, where does that signal go to? Well, I want to emulate what happens in this tube over here, the mixer. Remember, I said that one of the functions of the mixer is to create a signal which is 460 kilohertz, the IF frequency, above what's coming in. Now, I don't want to use what's coming in. I want to produce 460 kilohertz and pass it through these IF transformers and the IF amplifier and make sure that it's going through smoothly. It's going through cleanly as possible so that I can get a nice result at the end where 460 is the center of a bell curve, which I showed you previously, right? Now, the way to do that is I can feed that 460 kilohertz right into the input of this tube. In other words, I can feed it into the grid of this ECH81 because, as I also said in a previous episode, the frequency that's produced by this mixer is the first frequency that comes in here, the one that the oscillator produces, the sum and the difference. So if I feed this in here, this one goes straight through, okay? It's one of the ones that goes straight through. Then I can tune these coils, this one down here and this one down there, to make sure that I get it coming through to the detector as cleanly as possible. Then what happens is that at this detector, at this diode, the signal that's coming in here gets passed to there. Coming in here, passed to there. It's an AM modulated 460 kilohertz. So 460 kilohertz carrier comes through. I've optimized for that frequency, so it's coming through well, and it's modulated. And then when it meets the diode, it really rectifies it. It rectifies it and produces, if you get an AC voltage, you know that if you put it through a diode, you get rectification, okay? And the way this is set, it rectifies negatively, okay? So what happens is you get a negative DC voltage with the audio superimposed on it. It's not just the audio that comes out of here. It's actually the rectified voltage that comes out of here. It comes out as a DC voltage, which is negative, and also a audio tone. Now the audio tone then goes through to here to the audio stage, but the DC voltage is very useful because it's used to create a DC voltage, which is called the AGC, the automatic gain control voltage, which then gets fed back. If you see it going through here, gets fed back. It actually sort of charges this capacitor up. This is the AGC capacitor, and then it goes back to the grid of the tube. Now what happens if it's very negative? It makes that more negative, and that means the gain of this tube reduces. So if you have a very strong station coming through all the way through, it creates a bigger DC voltage, which then goes out that way, goes there. It's a negative DC voltage, so it makes this more negative, and it makes the gain of that lower, so the signal is sort of flattened out in terms of gain. If it's a weak signal coming from the front end, The weak signal goes through all that stuff, produces a smaller DC voltage, negative. So that smaller DC voltage, negative, across that cap, then goes back into there, and it doesn't cut out that tube as much. Okay, that's how you work the automatic gain control. Now this capacity is very important because this is another way of aligning the IF for the AM, but I'll get to that in a second. What I'm interested now is I'm going to feed the 460 kilohertz tone or carrier with the tone into here, and it's going to go through all that. I'm going to align these two, I'm going to align these two, and then it's going to come out of here, it's going to produce audio, it's going to go through the audio amplifier, through the power amplifier, through the output transformer and out the speakers. And I can measure the amplitude of that audio. And what I want is to produce the loudest or the biggest tone being carried by the carrier at the speakers. And then I know that I've optimized that IF transformer and that IF transformer because I have smoothened the path through for that carrier to go through. Okay, that's what we're going to do. That's one of the ways of doing it. Now, you might say, okay, if I'm going to look for audio tone, I can align this without a meter. I really can. I mean, what I'm getting here as an audio tone is a 1 kilohertz tone. It's an AC voltage. It's an AC signal. So I can measure it with an AC multimeter, right? And that's what I use. But if I've got good ears, I can just play with these things till I get the best volume possible. And that is one way of doing the alignment. And some of the old timers could do it better than using a meter. They just listen to the tone or listen to a radio station. You didn't even have to feed a 460 kilohertz signal in here. You could actually just listen to a station that was being picked up by the front end, a strongish station, and you can, or actually a weak station, and you could do the alignment till you hear it best at your speakers. And that's one way of aligning. It's a valid way of aligning. There's nothing wrong with that. But we're going one step further. We're going to feed the tone at the front end. We're going to measure the output here across the speakers with an AC voltmeter, and we're going to do the alignment for the highest peak. Now, just before that, I want to do something else. Remember I told you this produces a DC voltage, a negative DC voltage, which is proportional to the strength of the signal. And that comes through and goes all through there to the AGC cap. I can actually do a frequency sweep across the front here. So I know my peak should be at 460 kilohertz, but what if I put 440? What will happen when it goes through there? Will it still be heard? Probably, but the DC voltage will be lower. So the DC voltage that comes out here, through there, the AGC voltage will be lower. And I can measure that. If I take this to 460, it should be highest. If I take it to 470, it should come down again, so it should be lowered. Now, if I measure this with an oscilloscope, and I put a signal here that sweeps from, say, 30 kilohertz below the IF frequency to 30 kilohertz above, so if I put this, the center of the signal, the sweep, at 460 kilohertz, and I give it a span of, call it 60 kilohertz, this frequency is going to go up and then down, or rather it's going to go up, 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 and then start again, up, 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 up. It's going to go from 430 all the way to 490, then it's going to start again at 430, 490. That is a sweep. What happens here is that it detects a weaker signal because we're off tuning, as it were. It goes stronger, 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 then it starts coming down again. And that curve, that bell curve, which I showed you just previously, is going to be measurable or detectable at this capacitor. What I'm going to do before I even start aligning with the multimeter over here and with that fixed IF frequency over here is I'm going to give it a sweep anyway so we can have a reference and know what difference this aligning makes, because I don't know if it'll make any difference. I know that I twiddled one of these by mistake when I was trying to play with the FM. Remember, I showed you an example of how you can align the FM, and I know it was in this IF transformer, but I'm not sure if it was the primary or the secondary, and I think I got the cause wrong, so I did twiddle this a bit, and then I put it back as close as I thought it was, but we'll see if it makes any difference. So let me do that first. I've got the radio on. I've got the center of the sweep at 460 kilohertz. I've given it a span of 60 kilohertz. I've switched it on. And I've got the trigger. This has got a trigger signal that will indicate the start and end of the sweep going to one of the channels of the scope, to channel 4. And that's what I'm monitoring on the scope at the moment. So if I I need to get the time right. The time I've given it at 140 milliseconds, and I know that my scope is 14 divisions. So if I put this at 10 milliseconds per division, I get the start and the end of the sweep going through there. So the entire sweep is going to cover that, the scope. It's a linear sweep. Now if I put the volume up, you can sort of hear it sweeping, but I'll put the volume down. We don't need to listen to it. Now what I'm going to do is I'm going to monitor that capacitor on the scope, and I'm going to try and do this carefully because I do not want to get shocked. I'm measuring the top of the AGC capacitor, and the other side of the scope goes to ground. Now where are we? If I put on channel 1, there it is. Okay, my scope is being triggered on with the trigger signal. I'm going to make this one, well, actually I'll leave it there for now. I need it to trigger, but I'm going to play with I've made channel 1 DC coupled, and I'm going to play with the amplitude because I want this as high on the screen as I can. And that sort of gives us an indication of the tuning. Now, I don't totally trust this because this means that the shape is not absolutely correct because that capacitor actually distorts it, and it depends on how fast you make the sweep. So if I make this 70 milliseconds, let's see, time, where are we? 70 milliseconds. Then I have to change this, and you can see it changes the shape, which means that my time factor, how quickly I change this, is affecting my shape. If I go to, 280 milliseconds, and I make this, I need to get the entire shape in there. It'll be 20 milliseconds per division. There we go. Drop that down a bit because it's too high. My shape changes again. So I'm going to use the 140. I like the 140. I don't really make this I don't take this as absolute gospel, but there's the shape, okay? And if I put this down here, just to get a reference, I'm sitting at, what are we at? 200 millivolts per division, and it's coming up from the bottom, 1, 2, 3, 4. So I'm getting a peak there of about 800 millivolts. That'll be my reference for the next stage. Once I've done this, I'll do the sweep again, and we'll see if we made any improvement. What I've actually got here is a little amplifier. It is a multiplier, so it takes whatever voltage is coming in. This is directly across the speaker. It's multiplying by, actually probably a bit too much. This is by 2. It's by 10, I think it is. And I've got it on 10 volts RMS AC. So that gives us a good deviation. And I've got this on dummy load, so you can't hear it. But if I change the volume, you can see it going down. I've got the volume on max. And now I'm going to peak this till I get the highest voltage on there. I know it's these two at the top and those two at the top because I've checked the schematic. So let's see what happens. Whoa. Whoa, this is going up a lot. This is going up a hell of a lot. In fact, more than the meter will take. I could change the range of the meter, but I'm just going to give it another 3 dB of attenuation here. See, that's too high. Let's give it, just changing the attenuator settings. So I'm making the signal weaker. So something was wrong here. Oh, there's a peak. That's a peak. Try that one. Okay, I've got this on medium wave. This is the primary, the secondary now of the first IF. That is still too strong, so I'm going to give it another, call it another 12 dB. Another 9 dB. I like it in the middle. There's my peak. Let's go back to this one. There's my peak, and now What about these guys? These are the other two. This one was pretty much there. It's pretty much there. Let's see the other one. That's the second IF. Whoa. There's my peak. Now I'm going to do it again, make sure that I've got it as peaked as I can, with the lowest signal that I can achieve and still hear the tone or see the tone on the scope. There's my peak. And there's my peak. And that's all there is to it. That is literally all there is to it. I've peaked the IF path through here, so 460 is coming through optimally, and that should have my IF for the AM perfectly peaked. Now, what has it done to the shape of our bell curve? I've got this set again for the sweep. Now, let's see what happens. I've got the measuring the AGC voltage across the AGC cap again, and we can see that because we've reduced the amplitude, the AGC curve is very flat. That's the yellow one you see down below. So I don't need to worry about, in fact, I want the AGC to kick in so I can increase the amplitude of the signal. I'm taking away those attenuations that I had. Probably a bit too much there, right? I do remember I had this at 0 attenuation when I was doing it originally. So I'm going to reduce the volts per division quite a bit. And now I'm at 1 volt per division. I seem to recall that we were at 200 millivolts per division. Now look at that. That is an optimized curve, which doesn't look too optimized, does it? This is why adjusting it on here is actually a little bit tricky. If you try to adjust it, you can, and I'll show you the result. If you look at the scope, this is what happens if I start adjusting this. I can theoretically get a nicer curve than that, but I'm not so sure that it'll be perfectly peaked. See, that's moving that way. I need to play with these guys. This is what they used to use a wobulator for, but the wobulator used to work at, I think it was 1/60th of a second. It was 60 hertz. So I can go backwards and forwards and play with that. And what's going to happen is I'm going to shift this somewhat, and I can probably get the curve to look nicer. Let's see, if I make this 280 milliseconds, in fact, if I make it slower, let's see, where's that? That would be 280 milliseconds. There's a bit of sort of oscillation starting at the beginning there. If I make this 50 milliseconds per division, that means I need to make that 700 milliseconds to go right across the span. And it starts looking better, doesn't it? It's sort of looking better. Let me give it a bit more. So I'm giving that capacitor more time. I'm increasing the volts per division here to get a nice... I'm giving that capacitor more time to charge and discharge. Discharging is just as important as charging. Now, watch this. If I take the span, at the moment is 60. If I make it 40 kilohertz, give it time to settle, that's what happens. If I make it 20 kilohertz, that's what happens. Now, it's not centered, is it? Again, this is where it gets tricky, because I'm not sure that I'm doing it any good by trying to center it, but I'm going to try anyway. Come on. I've got to do it slowly because I've got to give it time to settle. and for the sweep to take effect, I can make it closer to the center, which is a 460, but then it drops the amplitude. It's making it sort of rounder. That's looking much better. That's sort of peaked it right on the center. That is spot on. Now let's try something else. Let's try make it even slower and see what happens. I'm going to make this 100 milliseconds, so I need to give it 1.4 seconds to go across the screen, and it takes a while to acquire. That's perfect. That is perfectly aligned visually. It's a very even bell curve. It's uniform left and right. And that's how I'm going to leave it. Now that was the, let's call it the more technical way of doing it. We're using what they would call a wobulator. I'm just using a sweep generator. And it's no big deal, because the advantage with this is that you're not actually hearing the sound. You can put the volume down low. If I change the volume here, it makes no difference. You're not hearing it because it's going through the dummy load anyway. But it makes very little difference. It makes no difference to the actual AGC. In fact, what it did do, I think this thing was overloading the output because the signal was so strong. So that, see that? Wait a minute. It was sort of oscillating because, there, you see that? That was actually because I was overloading the output because the signal was so strong that it was creating oscillations. That is a perfect bell curve. And if I go one step further and I want this to look better, I can go to channel 4, which is the, channel 4 is the trigger coming in, and I can make it invisible. There we go. So I'm using that fourth channel as a trigger, and it is triggering, but it's not visible, so I can just see my, my bell curve. So that is now perfectly aligned, or as perfectly as I can. There is one caveat, and that is I'm not sure just how much the AGC cap itself is affecting the delay on that thing, but I've had no problems in the past using this method. This method is a little bit, actually it's easier for me because I've got the equipment and I've got the, since I've got the output going to the speaker in there, and then that's my load controller, so I can make a dummy load or speaker. I've got a read off straight from there to one channel of the scope. This is actually easier for me than setting up all the multimeter stuff. But I must admit, I really do love the moving coil meters when you're adjusting, because you can see it move across. It just makes it a lot easier, and that's what I normally use if I don't want to do the sweep version. So the result, my friends, is I've shown you how to do the IF alignment. In essence, we've got basically three methods. Method number one, you just take a strong station and you tune it till you hear the best signal possible. That works. It works. You're doing what the meter was doing. You're just using your ears to determine what the strongest signal is. You're not going to worry about the shape of the curve or anything like that. You just tweak these. Make sure you only play with the AM IF transformers. You tweak them till you get the best audio signal. That's your IF alignment for AM adjusted. You've got to have it on medium wave, long wave, or short wave. Normally you leave it on medium wave. So that's your IF alignment done. Second option is you feed a signal into here, into the grid of the ECH81 at the IF frequency, 460 kilohertz, with a tone on it, and you adjust it till you get the highest amplitude of the tone, measured with an AC voltmeter, or you can actually look at it on the scope if you got one. Third method is you use a sweep, which is you're sending a sweep signal into the grid of the ECH81, where the frequency coming in is sweeping from a span below the IF frequency to a span above the IF frequency. You've seen what I've done there. I've made the span wider and shorter, but you can adjust it that way by tweaking the IF transformers to get a nice curve. That's the other way of doing it. That's the way I'm going to leave it for now. For the tone version, where you're feeding in the carrier with a tone, make the amplitude of that carrier as small as possible so that you don't have your AGC kicking in and affecting the gain of these tubes. You want it as small as possible. You want to just be able to hear the tone and to be able to discern whether it's going up or down on your meter, but you make it as low as possible. And for that, I've used my attenuator over there. The other thing is the stepped attenuator's got a capacitor between the input and output, so this is capacitively coupled. You don't want to connect your signal directly to there, directly from your signal generator. You put a capacitor in between, so it's capacitively coupled. It doesn't throw off the bias. That's important. And essentially, that's it. That's the IF alignment of the AM. And the reception on this thing should be greatly improved because, as you saw, the curve at the beginning was at a very low amplitude, and at the end we've got a nice curve, which you can still see on the screen there, and it's a much higher amplitude because the volts per division is a different range altogether. It's really a very, very good sign that this radio is going to improve in terms of reception quality, because we've had an effect when we adjusted these. Admittedly, when I adjusted these two, it made a big difference. And I did tweak one of them or both of them when I was trying to find the FM one. This one I hadn't touched much, and as you saw, there was very little adjustment needed there. So I think I might have been the one who affected that myself. So this is where I'm going to leave you for now. And I've got some equipment to put away, and I've got to try and get rid of this COVID, which I'm suffering from. But I do hope you've enjoyed that and you learned something. And if you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Once again, thanks for watching. Bye for now and stay safe.